Hello, my name is Knowlton Olmsted. I'm a senior engineer at Amcor Technology and have been working on development for advanced automotive packages, specifically focusing on achieving AEC Q-100 grade zero reliability in our flip chip BGA and flip chip CSP packages. In this presentation, I will discuss the unique material and reliability challenges presented by the grade 1 and 0 requirements and our approach to solving these problems. With modern automotive electronics controlling critical user interface and safety functions, the lifetime requirements for automotive packages is much longer than for typical consumer products. Standard requirements are zero defects in a 15-year lifetime with up to 10,000 operating hours and 300,000 miles driven. Looking beyond the standard lifetime requirements, we know modern electronic vehicles will require the consideration of extended operation times for many components during charging periods and with preconditioning features being available in some vehicles. The introduction of self-driving vehicles, especially for commercial applications, will significantly extend these lifetimes, with some vehicles likely requiring over 100,000 hours of operation time over their lifetime. The table below lists the current temperature cycling and high temperature storage reliability requirements in the AEC Q-100 specification. The target grade for a component is identified by the operating temperature range it's expected to see during its lifetime. For grade 1, this operating temperature extends up to 125 degrees Celsius, and grade 0 is for components expecting to see temperatures up to 150 degrees Celsius. With the higher operating temperatures at grade 1 and 0, the temperature cycling and high temperature storage reliability requirements are correspondingly higher, with temperature cycling ranging from minus 55 to 150 degrees Celsius, and high temperature storage increasing up to 175 degrees Celsius. Note that the AEC Q100 specification provides an option to test high temperature storage at either 175 or 150 degrees Celsius. This is fairly significant, as I'll show later on that certain failure modes tend to appear at 175 degrees C that do not show up during 150 C high temp storage at the same grade. Because of the high confidence needed in automotive reliability, it's not uncommon for a grade 1 part, for example, to be tested during a qualification out to twice the target grade. In this case of a grade 1 part, this would mean testing to the grade 0 specification, and for a grade 0 part, this would mean testing to twice the cycles and hours of high temperature storage listed in the grade 0 row. With 150 degrees C high temp storage extending out to 4,000 hours in this case, or almost 6 months, this really highlights the need to develop methods of material characterization and simulation that will help identify and screen material sets with a high likelihood of success before committing to such a long development cycle. Now I'd like to discuss our flip chip BGA packages and the challenges we have encountered in grade 0 reliability testing, along with sharing some of the characterization and simulations that we have done to help identify a suitable bill of materials. As more integration is and will be needed for sensors, ADAS, infotainment, and communication within and between vehicles and infrastructure, demand is increasing for larger package sizes that still meet grade 1 and 0 reliability requirements. Because of the large CTE mismatches between the die, heat spreader, and substrate, this poses unique challenges for achieving temperature cycling reliability, where the stress generally increases with larger body and die sizes. The large material property mismatches will often result in cracking at the substrate, bump, and underfill. In addition to these thermomechanical challenges, a number of material challenges present themselves in high temperature storage. Oxidation of the capillary underfill surface at the die edges can result in cracking around the underfill fillet. These cracks can grow to the die edge or substrate and cause further damage. In a use case condition where high temperatures and mechanical stresses are combined, these cracks could also result in eventual mechanical failures. The increased solder diffusion and resulting growth of copper-tin intermetallic compounds is another area of concern in high temperature storage, especially at 175 degrees C. Early in our development, we performed multiple simulations to help narrow down the materials and properties that would have the largest impact on package reliability. This was done by modeling a range of properties for each material and evaluating the resulting stress for several failure modes, including metal pad stress, stress in the loci dielectric, the interfacial stress between the solder mask and underfill, and room temperature warpage. The simulation results allowed us to create sensitivity plots which visualized the relative impact of material property variations for the different modeled materials on the stress in our area of interest. The plot on the bottom right of this slide shows an example of our stress sensitivity plot for the metal pad stress. You can see the largest factors to affect the location. Stress increases as the modulus of the buildup increases. Similarly, increasing the CTE above TG for the underfill will increase stress, while increasing the underfill modulus decreases the metal pad stress. This method of simulation provides us with an early picture of the relative impact for each material property on different areas of the package, so we can focus our efforts on identifying suitable materials that will have the largest impact on overall reliability. After completing the simulations, the buildup, underfill, and solder resist materials were selected for further characterization by measuring how their material properties changed after exposure to typical temperature cycling conditions. For our analysis of aged flip chip BGA material properties, we subjected material samples to the temperature cycling H condition, which cycles from -55 to 150 degrees C at a rate of 2 cycles per hour. Bulk material samples were created in collaboration with our suppliers and were placed in a temperature cycling chamber. The CTE, modulus, and TG of each material was measured at time 0, followed by additional measurements of the aged materials at 1,000 and 2,000 cycles. The 2,000 cycle measurement corresponds with the grade 0 reliability requirement. The results of our material aging experiment are shown in this slide. Each graph shows the values for one material property as it changes over the course of temperature cycling for each material. Each line represents the measured properties for a single material. Two materials, each of buildup, solder resist, and underfills were evaluated. And for our buildup materials, no change of modulus was measured after temperature cycling. Both buildup materials showed decreasing CTE1, and the selected materials showed opposite trends for CTE2, with one material CTE2 increasing and the others decreasing. The glass transition temperature of both materials increased over the course of testing. The solder resist materials showed some of the largest property changes throughout the testing, with the modulus increasing by almost 40% in each material after 2,000 cycles. TG and both CTE1 and 2 decreased during cycling. The underfill material was shown to be relatively stable during temperature cycling. One important note to make here is that the underfill was cycled as a bulk sample, and material was extracted at each read point from the bulk sample for property measurements. So any of the oxidized surface of the material would have been removed while the sample was being prepped for the property measurements. This gives us a clean measurement for the bulk material property changes during cycling, but not of the outer surface, which is exposed to oxidant. After the results of our simulation and material aging experiments were collected, A test vehicle was designed to evaluate our substrate and underfill materials selected for a grade 1 and 0 package. The material selection was made based on their properties and using the sensitivity analysis simulation, and also based on the results of the aging experiments, where some materials showed greater stability than others. The test vehicle was designed as a 35 by 35 millimeter package with a 15 by 15 millimeter die size and 150 micron pillar pitch copper pillar interconnects. The substrate was an 8-layer design with a 0.4 millimeter core. We also included one leg of substrates in our DOE with an ENIPIG surface finish to evaluate the bump reliability in high temperature storage. Multiple underfills were evaluated to investigate their susceptibility to the surface oxidation and cracking at 175 degrees C, which had been previously seen sometime after the grade 1 HTS read point. The next few slides will detail our results, but to summarize, we have identified a BOM suitable for grade 1 reliability, and the same BOM meets grade 0 temperature cycling requirements, with really the only remaining issue being the underfill surface cracking that we see at 175 degrees Celsius. At 2,000 hours of 150 C high temperature storage, which is one of the conditions for grade 0 reliability, the no underfill cracking and solder voiding issues are observed. This suggests, as we'll see when we look at the 175 C data, that the activation energies for these high temperature failure mechanisms are such that half the HTS time with a 15 degrees C increase in temperature is not the equivalent of the lower temperature conditions. So the image on the left shows a cross-section of the underfill fillet after reaching the grade 0 condition at 175 degrees C. Visible cracking is seen extending from the surface into the oxidized portion of the underfill. In the areas near the die edge, the crack will sometimes propagate along the die. Although these cracks did not result in any die or substrate cracking and no electrical failures occurred because of the underfill surface cracking, this is still an area of concern when considering the long lifetimes required for automotive packages. In addition to the underfill oxidation, the high temperature resulted in increased solder diffusion and a very thick intermetallic layer on the substrate pad, with solder voiding being a resulting issue. In the case of our substrates with the ENIPIG surface finish, this failure mode was not observed. Now I'll discuss our flip chip CSP packages and the challenges we've encountered in grade 0 reliability testing, along with sharing some of the EMC characterization we have completed to help identify a suitable bill of materials. In our flip chip CSP packages, the challenges we encountered were primarily related to material degradation in high temperature storage, similar to our flip chip BGA packages. In the case of a flip chip CSP package, a capillary underfill is typically not applied after the die attach process. Instead, a molded underfill material is used, which experiences similar issues to our flip chip BGA capillary underfills, that being oxidation and cracking. However, in the case of our flip chip CSP packages, the target reliability condition we are aiming to achieve was twice grade 0. So this means our high temperature storage testing extends out to 4,000 hours at the 150 C condition. Because of the smaller body and die sizes in flip chip CSP, the mechanical stresses caused during temperature cycling were less of a concern here. Our baseline material set was sufficient to pass 2x grade 0 temperature cycling, and additional materials selected to address the degradation issues did not decrease the temp cycling performance. Like the capillary underfill materials in flip chip BGA, the main challenge with our molded underfill, or EMC, is oxidation and embrittlement at the surface, which leads to cracking during high temperature storage. For flip chip CSP, when the EMC crack occurs over the die area, this can lead to associated die cracking. As in our flip chip BGA packages, accurately predicting the reliability impacts of a new material requires an understanding of how the material properties change after prolonged exposure to high temperatures. In this evaluation, several EMC materials were evaluated after high temperature storage at 150, 175, and 200 degrees Celsius. The motivation behind the 200C condition was to determine whether the characterization period could be reduced by increasing the rate of degradation without fundamentally altering the failure mechanism. Bulk EMC samples were created, and the modulus, CTE, shrinkage, and flexural strength were measured at various points during the HTS testing. In addition to the material property measurements, we collected data on the penetration of oxidation by sectioning the sample and imaging under a fluorescent microscope. The images on the right show an example of the EMC cross-sections under the fluorescent microscope after 2,000 hours of high temperature exposure. In the samples exposed to 150 degrees Celsius, there's a clear distinction between the outer fully oxidized surface and the inner layer in which the oxidation reaction is still occurring. This region is thinner at the 175 degrees samples and hardly visible in the 200 degrees samples after 2,000 hours. It's interesting to note in EMC-B that the oxidation thickness of the 200 degree sample is actually less than at 150 degrees Celsius. Multiple other EMCs that we evaluated with this same property were identified. Modulus and TG measurements of the samples show that as the material becomes oxidized, or the outer surface of the material, the transition between its glassy and rubbery states becomes extended over a very wide temperature range. The result of this extension is a large mismatch in the modulus, specifically near the temperatures where high temperature storage testing is conducted, that being 175 and 150 degrees C. The non-oxidized portion of the material is well above TG and will have a modulus of almost 0, whereas the portion that becomes oxidized will have a very high modulus at the same temperature. This mismatch in material properties that develops over the course of the high temperature storage testing is hypothesized as one of the contributing factors to the surface cracking that we observe. In addition to material property measurements, the shrinkage of the EMC samples was measured throughout the HTS testing. Because the shrinkage is expected to only occur in the oxidized layer of the material, it was hypothesized that a material with low shrinkage would improve reliability. Following the material property characterization, multiple EMC candidates were selected for a DOE with the goal to mainly eliminate the EMC cracking and reach the 2x grade 0 reliability conditions. Our test vehicle was a 12 by 12 millimeter squared body flip chip CSP containing a 7 by 7 millimeter squared die with staggered 45-80 micron pitch copper pillar bumps on a 4-layer embedded tray substrate. One high TG EMC material was selected along with other materials that showed low shrinkage and good oxidation behavior. Another criteria considered when selecting EMCs was how stable the material properties were during high temperature storage, regardless of their base values. However, this criteria was difficult to utilize as there was a fairly wide variability in stability between different material properties and the EMCs. 3 candidate EMCs passed our 2x grade 0 requirements for both temperature cycling and high temperature storage with no electrical failures or EMC cracking, indicating our selection criteria is well suited for evaluating EMC materials for flip chip CSP packages. So in conclusion, for our flip chip BGA packages, we have developed a good grade 1 bill of materials. The same bill of materials meets the grade 0 temperature cycling requirements, but eliminating the underfill cracking that occurs at 175 degrees C high temp storage remains a challenge, and this bill of materials doesn't show those same challenges in the 150 C high temp storage condition. Our flip chip CSP package has passed qualifications out to 2x grade 0 with multiple EMC materials, thanks to the early material characterization that we used as a tool to identify suitable candidates. One thing that our reliability testing has shown is that the grade 0 high temperature storage conditions for either 1000 hours at 175 degrees C or 150 degrees C for 2000 hours are not necessarily equivalent, with the 175 degrees C requirement being much harsher and resulting in material failures that do not occur in the 150 degrees C condition. We've also shown that simulation and material characterization is an important and critical step in developing and evaluating new material sets for automotive packages. This allows us to identify key parameters and potential materials, screen potential materials, before building parts for reliability testing. This process should help to reduce the time required to solve new problems as they arise for future automotive packages, as those packages increase even further in size and complexity. Thank you for watching.